This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. Electricity is the backbone of modern civilization. Nearly everything that people depend on in our daily lives requires a highly reliable supply of electricity. From the devices we use for work and entertainment, to the network of refrigeration supporting the nation's food supply, or keeping the lights on and medical equipment running in a hospital. In recent years, the electrical grid infrastructure is seeing additional strain as longer and stronger heat waves increase demand and result in system failures and blackouts. We are joined by Kyri Baker, assistant professor in the Civil, Environmental, and Architectural Engineering Department at the University of Colorado Boulder, where her research is focusing on optimization and control techniques for electricity markets, power grids, and buildings. Professor Baker, thank you for joining us today.
Thank you for having me.
So how did you first become interested in electrical engineering?
Well, my dad's an electrical engineer, so I kind of grew up around circuit components everywhere in the house, and he was also a professor, so I got to visit his lab and talk to his students, and even at an early age sit in on his classes, which was really fun. I didn't understand them, obviously, but it was cool to see, the impact that electrical engineering could have and the impact that a professor could have. So that really inspired me. And then when I started building little circuits on my own, seeing LEDs light up, it really solidified the fact that I could do something cool in this field.
Approaching power grid work, I think we need to define what the power grid is and kind of do a little myth busting on how broad spread or how unique parts of it are.
Yeah, the power grid means different things to different people, but for me, it has three pieces. So the generation, transmission, and distribution. So the generation is like power plants, large scale power plants usually. Transmission are the big power lines, so like the huge metal towers. And the distribution are the smaller poles and wires that take power to your house. And so the power grid kind of ends when it reaches your home or the electricity meter. That said, there's different types of grids. There's, microgrids, which are little isolated versions of this, nano grids, even things called picogrids. So depending on who you talk to, power grid means different things, but it always encapsulates generation and some kind of distribution of the power.
Right. And I think when people hear about it going down, they're not necessarily sure what it means. I think getting into some.
Yeah. Yeah. Sometimes it's a power plant going down. Sometimes it's a wire going down.
What is optimal power flow?
Optimal power flow is basically, can we direct the electrons in the grid in a way that minimizes the cost to deliver power to consumers? So traditionally, this OPF problem, as we call it, optimal power flow, is minimizing cost of generating power and subject to a lot of physical constraints. So power lines can only carry a certain amount of current through them before they start heating up. This is the same concept as the circuit breakers in your house. If you plug in 3 hair dryers into the same bathroom circuit, the breaker is going to pop so that wire doesn't overheat and, sag or cause an electrical fire or a short. So there's different definitions of optimal power flow that are sort of arising. Some people think we should minimize carbon. Some people think we should minimize losses. But the core problem has always been about cost.
So what are some of the traditional problems with optimizing the grid or power flow?
The grid is extremely complicated. We don't have full visibility over everything at a given second in time. So optimizing power flow in the grid basically means we're making a bunch of approximations to solve the problem fast enough. And we're making approximations in the sense that we don't have situational awareness everywhere. So in some cases, utilities, for example, don't even know exactly where all their transformers or poles and wires are. So this is an old system that's been operating for a long time. It's going through a makeover, so to speak. And operating it is very, very hard. You have to balance supply and demand within seconds. So it's not like other types of networks. Like, transportation networks, the traffic can just slow down and you're still stuck in your car, right? Nothing terrible is going to happen. Water networks, the water can be stored in the pipe. In a power network, you can't store electrons in a wire in the same way. They lose their energy if they're not flowing. So power is inherently just a faster time scale, extremely challenging system that we rely on for our everyday lives.
everything pretty much at this point.
Yep.
And speaking of that, what kind of failures, I guess, cause blackouts?
Blackouts are caused by so many different things. I mean, the simplest one that we've all probably experienced is blackouts from high winds. So a tree blows into a wire or a power pole gets taken down. We just saw this with the hurricane near Houston. A bunch of those power poles were just uprooted or a tree branch fell on the wires, causing a short. So the power doesn't flow to consumers. The power flows through the tree to get to ground, which is a more efficient path for the electrons, from the electrons' perspective, you could say. But there's also things like, we don't have enough generation. So during not to bring up Texas again, but during the 2021 winter freeze in Texas, there was a lot of issues with natural gas wellheads freezing and other power grid components just physically unable to produce power. So it can happen on the generation side. It can happen on the transmission side. The 2018 Camp Fire in California was a rusty transmission hook. It snapped during high winds and it sparked against the tower, causing one of the most costly disasters in California history. So failures can happen anywhere, unfortunately.
Right. Problems of an aging infrastructure to a certain extent here.
Yeah.
Moving into kind of modern tools that are being involved, how are artificial intelligence and machine learning assets kind of making the modern power grid more manageable?
Well, currently, AI and ML, artificial intelligence and machine learning, are used a lot for forecasting. So forecasting is huge in power grid optimization. If we know what to predict, we can better prepare. So a lot of these conventional forecasting models can't take into account as many variables as, like, let's say a neural network or some other AI-based model can. So AI is really good at synthesizing down a ton of different inputs, figuring out the relationship between those inputs, and then predicting something that it's best guess for what's going to happen. And so forecasting is a really good one. You can also use AI for predicting failures or faults in the grid. So when is a component aging going to actually result in that component failing? So being able to predict those failures using AI, again, by just using a massive amount of data to uncover relationships that humans can't, just because it's simply too complex. And then the final frontier, I guess, of it using AI in power grids is to actually operate the grid. So that's where my research comes into play, is can we actually operate the grid on faster timescales more reliably by using data we've collected in the past? So not running the same model, from scratch every day, but actually learning from how the model has behaved in the past, maybe tweaking it or training it offline with scenarios that haven't happened yet but could happen, and then using that model to assist human operators to operate the grid more efficiently.
Can we explore that area a little bit more? Like, what are you finding in running these kind of models?
So the AI-based models have pros and cons. So the pros are that it can solve this big optimal power flow problem extremely quickly. We're talking, 1 second, which means this balancing supply and demand issue becomes a lot easier when you're using an AI-based model. The negatives are if the model wasn't trained on data that, it's seeing for the first time, you can encounter issues because the physics aren't necessarily embedded in the neural network in the same ways they currently are in the current software to operate the grid. So if you have a situation where, there's a risk of a blackout and we did not anticipate that and we did not include that in the data set when we trained the AI model, that model is going to perform really poorly. So it's good for speeding up kind of these typical scenarios that we encounter for most days. It's not quite as good for these rare occurrence situations that we sometimes have to deal with.
Right. Thinking about when the hurricanes are coming in and how
Exactly.
we manage that in real time. So are these kind of tools being used out in the real world yet?
As far as I know, not a lot of the operational tools, mainly because of some of the risks that I mentioned earlier. We don't really want to change the way this system is operating because it just affects, hundreds of millions of people. It is being used in real grids for forecasting, though. So that's like we can compare the results offline, we can prepare the grid, but it's not directly controlling a power plant or a battery. So it's a little bit safer to use it for forecasting.
Absolutely. Okay, so one of the things I saw in your work is kind of considering how renewables are folded into the existing grid system. Can you tell me a little bit about the complications that pop up when you try to do that?
Yes. So renewables are great because, obviously lower operational carbon. They don't use fuel often, so you can make them more distributed. I can put solar panels on my rooftop, but I can't necessarily put, a coal plant in my house or even, a natural gas generator to the same extent. So a lot of these things are just great. They solve a lot of problems in the grid. That said, they do introduce a lot of issues with this supply and demand balancing, because we can't control exactly how much power a solar panel is producing or a wind turbine. We can more so with hydropower, which is why hydropower is great. It's just geographically limited. So the supply and demand balancing is really the core issue here. When you have large power plants like nuclear, coal, gas, they have this natural spinning behavior that they do. It's a turbine often spinning. A lot of them are steam turbines, which means, you put the coal in, you light it on fire, that heat boils some water, and that water turns into hot steam that turns a turbine that then generates electricity. So that turbine generates electricity, and then if people start consuming more, the turbine naturally starts to speed up to accommodate. If people start consuming less, it'll have to slow down to accommodate. And that's natural mechanical behavior for that piece of equipment. But if you get something like solar panels, they don't really have moving parts in the same way. They're basically just converting photonic energy into electrical energy. And so we have to tell it, when to produce less or when it's okay to produce more. So there's a little bit more nuance with, the grid's not going to balance itself in the same way it has been. It's going to be a little bit more challenging with renewables. So that's why it's so important to have algorithms and methods that balance supply and demand so quickly, because you can get a cloud passing over a solar farm that changes the supply side. Yes.
Do you think that we'll ever get to where there's good battery options for kind of grid level power storage?
We're definitely getting there already. If you take a look at Texas and California, they've installed a ton of utility scale batteries and small scale batteries in the past few years. The batteries obviously have some issues with materials, supply chain, recycling, end of life issues. But in general, those batteries provide a huge buffer for that renewable variability. And again, they have that benefit where you can make them distributed. They don't have to be a big coal plant connected to transmission only. You can make them small. You can connect them to people's cars, their houses, and the big transmission side of the grid. So batteries are great for grid stability.
Okay, so what can the average person do to change how they use energy as we're thinking about additional strain on the grid?
I think the first step is just education. I think a lot of people don't fully understand how electricity gets to their homes, which is fair because it's very complicated. But knowing that, a lot of these outages aren't due to renewable energy, for example, the majority of outages are just due to the distribution grid being old and extreme weather impacting the poles and the wires. So it's hard to sort of unpoliticize some of these issues in the energy space, which is always frustrating because at the core of it, a lot of them are engineering or technical issues that we're trying to solve. But things like, switching your gas-powered car to an electric vehicle, almost regardless of where you live in the United States, your carbon footprint will be lower. Unless you drive one of these extremely large, like Hummer EVs or something like that, then your carbon footprint may be higher from the EV. But, I'm talking life cycle emissions from the mining, the construction, everything. So transportation is a huge one, education. And then if it's within your ability, adopting clean energy technologies and learning about how you can replace gas appliances in your house with electric ones to help lower your carbon footprint.
There's been a kind of thread lately with different science people that also have musical interests. So I want to ask you about how creative arts, music, playing guitar, how does this kind of thing impact your work?
Yeah, I've noticed that pattern as well. It seems like people who love music and people who love engineering are often overlapped. I love playing music. I would say it's my number one hobby. I started with guitar. Just being able to play songs I heard on the radio was super cool. Being a rock star, just playing in my bedroom gave me some confidence that I didn't have before. And then during COVID, I decided to learn bass guitar. And I was like, this is, similar enough that I feel comfortable, but it's a different way to hear the same songs that I've been hearing. I start noticing different patterns. And then recently I started playing drums. And that has really, honestly, I would say changed my life, playing drums. It unlocks this new aspect of rhythm when I listen to music and when I even, hear things in the grocery store or things that I didn't pay attention to before. I start having this appreciation, being able to experience it on another level. And so it's very similar to engineering where it's like, I knew nothing going into it. I just decided to try something. And then I got in this, mindset where I was like, this is cool. I want to spend more hours on this. And then I go. And then before I know it, I'm, good at whatever it is. Engineering is the same way. I'll explore like a Wikipedia article and I'll be like, this sounds like it could be applied to power grids. And then I'll go down a rabbit hole and then I'll, think about something like, what if we don't solve optimization problems anymore? What if we just train models to learn the optimal solution? So that level of creative thinking is just necessary to do engineering and science. And music has helped me think in that new way of seeing things in a new perspective.
For you, is it technical? Because like some people will really focus on like the counting with music, I find. Does it kind of manifest in your head in that way, or are you more intuitive and kind of following your ear with it?
Surprisingly, I can't read music. I never learned how to read music. It's completely intuitive. I recently, last week actually decided I was going to learn a song on piano for the first time. I don't know anything about piano. I sat down. It was really hard for me to focus on learning how to read music. So I just started trying to mess around and intuitively figure it out myself. There's pros and cons to that, but that is also a way I like doing research. If you do too much background research ahead of time, it kind of biases your brain towards thinking that's how this problem should be thought about. Whereas you come at it with this naivete, you don't know what people have done, you might be actually in a better space to come up with a creative solution.
Right. There's a thought that I heard a lot when I lived in Los Angeles where people would be talking about that you don't know that you're breaking the rules. And I think that applies to any sort of endeavor, really.
Exactly. The downside of that is you think you come up with something amazing and then you search it and you're like, oh, somebody did this in 1865. That makes sense.
Or it's like a freshman year college course answer that you thought was really great.
Exactly. So that part does happen too.
Hilarious. Okay, so last question for today. What are the next steps with your power grid work?
Well, a lot of this stuff I've been focusing on so far has been about solving these optimization problems quickly to save cost. I think we're kind of moving towards a grid where there's a lot of low cost power sources. So it's going to be less about cost and it's going to be more about reliability. So I've been kind of thinking about, how do we solve problems that can address blackouts or reliability issues, or how do we harden the grid against climate change and extreme weather? So AI can help there as well, in addition to cutting costs for consumers, obviously, and cutting carbon. So thinking more about that reliability piece recently.
Special thanks to Kyri Baker. For the Discovery Files, I'm Nate Potker. You can watch video versions of these conversations on our YouTube channel by searching at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.